Welcome. In this video, I will be explaining what Kirchhoffs laws are and how we can use them to solve different problems involving circuits. Kirchhoffs laws are made up of two separate rules that can be used to analyze any circuit, whether it's complex or simple. Kirchhoffs' first rule is called the Junction Rule, and is an application of the conservation of charge. So first, I'd like to showcase this rule using a picture of the river here. As we can see in this picture, we have a large stream that splits off at the junction into two smaller streams, but no water is lost. Everything is conserved. Much the same as the river, whatever flows into an electrical junction must flow out. Or in summary, the idea that whatever charge flows into a junction must flow out. It is conserved. So if we look at this first example, we can see that I1 is 15 amps. And as it moves towards the junction, it hits the junction and splits off into two smaller charges, I2 and I3. I2 is equal to 8 amps and I3 is equal to 7 amps. If we plug it into this equation here, which is I1 equals I2 plus I3, we can see that I2 is 8 amps plus 7 amps equals 15 amps. And thus, all charge is conserved over the junction. The same works as if two smaller streams are flowing into one larger stream, as seen in example 2 here. We have an 8 amp and a 7 amp coming together at a junction and then flowing, and we see that it equals a 15 amp, and the equation works the exact same. Now moving on to the second rule, we have something called the loop rule, which is an application of the conservation of energy. To summarize this law, I would like to use the example of baking bread, which is the reason for this photo here. As we make bread, it starts out as all dough, but as we bake it, less and less of the dough is present and more of it becomes our final product, the bread. But the contents or ingredients in the bread itself stays the same throughout. In the same way, in a circuit system with resistors, there's a voltage drop over each resistor. However, the charge or current stays the same throughout. In this equation here, we are given EMF equals the current times the resistance of the first resistor plus the current times the resistance of the second resistor, etc., etc. From this, we learned that EMF is the total change in voltage, and that the total change in voltage is equal to and only equal to the voltage drop over each resistance. No other energy is lost. Everything is conserved. So, to demonstrate this, I would like to use this example here below. We see that the voltage drop over the entire system it starts at 20 volts and it ends at 0 volts. So that way we know that the EMF of the entire system is equal to 20 volts, or a change of 20 volts over the circuit. Now we can calculate the voltage drop over each resistor by using the formula here. So first we can go the current times the resistance of the first resistor. So we know that the current is 3 amps and the resistor's resistance is 2 ohms. By multiplying that together, we can see that there is a 6 volt drop. So it will come in as 20 volts here and end as 14 volts here. If we keep going around, we can see that, and keep applying this formula, we can see that it goes from 14 volts to 5 volts, and from 5 volts to 0 volts. Showing that if we add all these together, 6 plus a 9 volt change here, plus a 5 volt change here, equals 20 volts. And so from this, we can see that the energy was conserved throughout the system. Okay, now the cool thing about Kirchhoffs laws is that they can be applied to more complex circuit problems and help simplify them. So if we scroll down here, we can see we have an example here that has a 2 battery system. So we have a 12 volt battery on the left-hand side and a 5 volt battery on the right-hand side. And in this system, there's 2 separate circuits or loops. And each one is going to have their own EMF. So for this, we'll call the left-hand side EMF 1 and we'll call the right-hand side EMF 2. And so the first thing we're going to do here is we're going to use the loop rule, which is, as we talked about before, the EMF for change in voltage is equal to IR1 plus IR2. So we're going to look at this, and we can see that I've separated it into the left circuit and the right circuit. So we're going to look at the left-hand circuit first. And so we see that the EMF 1 is equal to 12. The change in voltage is going to be 12. So we're going to stick that there. And then what we're doing is we're going to be solving for the currents because we don't have those. So we can see that I2 is with a resistor of 4 ohms, which we put here. And then we have I1, which is here, with a resistor that's 3 ohms here. And then we're going to be solving for I1, and we're just going to leave that there for a second. Then we're going to move on to the right-hand circuit that has an EMF value of 5 volts. And just the same, we're going to see that the I2, or the second current, is going to be going across a resistor of 4 ohms, which we're going to stick here. And then I3, which is here, is going to go across a resistor of 2 ohms. And we're going to stick that right there. And then we're going to be solving for I3. Okay, now after we've solved for I3 here, we can take our I1 values, which we can find here, and our I3 value, which we find here, and we can plug it into the junction rule. Remember, in the junction rule was about conservation of charge. So at any of these junctions, there's 2 in this system, junction 1 and junction 2, all charge is going to be conserved. And so to solve for each of these functions, we can just, for each of the 3 currents, we can plug them into this system. And I've shown how to calculate I2 here. So we take the I1 value and plug it in there, and the I3 value and plug it in here, and our I2 is equal to about 1.5 amps. And as we continue to solve for each of these individually, we can see that I1 is equal to 2 amps, and I3 is equal to negative 0.5 amps. If you have time, I would recommend trying this on your own, seeing if you have any questions, and if you feel confused about a part, go back and rewatch part of this video. Thank you so much. As we can see that Kirchhoffs laws allow us to solve more complex problems through these 2 simple rules, and are exemplary of conservation of charge and energy in circuits. Thank you so much for watching.